Good morning, developers. We are going to tackle Project Euler number 3, and it involves trying to find the largest prime factor of this huge number. So this is totally not possible for a human brain. Python to the rescue. So I want to talk through what those vocab means. Make sure you know what a factor is, a prime number. We'll pseudocode it out. We'll go over to our code editor and give it a try. And if we run into an issue, hint, hint, we are going to, we will come back here and try and figure out what we need to update. So this will be the first one. Unlike number 1 and 2, which are pretty straightforward, you may not come up with the most efficient solution, but you probably don't need help if you want to just go through it yourself. This is one where there's a good chance you'll run into an obstacle. So let's take a look at this quick. The first thing we have to decide is what is a factor, because again our goal is to find the largest prime factor. This number, we'll look at the question again when we get to VS Code. But a factor, we saw this in problem number 1. If we take the number 4 for instance, what are the factors of 4? Well, a factor is any number that will divide evenly into 4. So if we take 2 and we take that into 4, how many times will 2 go? It'll go 2 times. 2 times 2 is 4. That gives us a result of 0. So we have 0 remainder, or we have no decimal places after. So 2 is a factor of 4. If we take 3 and try and divide it into 4, 3 goes in 1 time. 3 times 1 is 3. This gives us a remainder of 1, or 1.33333, or 1 1/3. So that means 3 is not a factor because we have a remainder. Again, remember in problem 1, we were dividing everything by 3 and 5, and if the modulus equaled 0, then it was a factor. Okay, so that's what a factor is. Our goal is going to be this. We're going to have this huge number, and what we're going to do is we are going to loop. So we'll do 4i(n). I'm going to put bn here for big number. Again, this is pseudocode. What we'll check is we want to know, is I a factor of bn? That's our first task. Is this even a factor? Well, how do we do that? We'll say something like if bn modulus I equals 0. That will be the determining factor. If it's a factor, right? It's a multiple, or it divides evenly, however you want to say it. This is our first task. And so if this is true, if it returns 0, then we need to know, is this prime? Okay, if this is prime, then we know that this satisfies our criteria because it is a factor and it is prime. So find out, is it bigger than what else we have used so far? How do we determine what a prime number is? Well, a prime number is kind of the opposite of what we were just doing. It has no factors other than itself and the number 1. So let's start, we'll look at the number 4 here. Is 4 divisible by anything other than itself? Because 4 divided by 4 is 1, and then 4 times 1 is 4. That gives us a remainder of 0. So the answer is always yes. 1 and 4 are always going to be factors of 4, but what other numbers are there? So what if we try and take 3 into 4? That goes in 1 time. We end up with 4 minus 3. We have 1. Okay, so 3 is not a factor of 4. We already saw 2. If we take 2 into 4, it'll go 2 times. That's 4. That gives us a 0. That means 2 is a factor of 4, which means 4 is not prime, because we can add to this list. There's 1, there's 4, and there is 2. Okay, if there's anything other than 1 and 4, 4 is not prime. What about the number 5? Well, can we divide 2 into 5 evenly? We cannot. 2 times 2 is 4. That leaves us 1 left over. Can we divide 3 into 5? We cannot. 1 times 3 leaves 2 over. And we cannot divide 4 into 5. That leaves 1 left over. Okay, so that means 5 has only itself and the number 1, which makes it prime. So that's how we're going to figure out if something is prime. What does the pseudocode look like? Well, we are going to take the number I, if we've determined that it's a factor, and we're going to do pretty much the same thing. We're going to do 4n in, we will start at the number 2 and we will go up to I. I we've determined is a factor. It's a factor of this huge number. Okay, so let's start at 2 and go up to that number and find out, is there anything divisible by it? So it'll be pretty much the same thing. If I mod n equals 0, then it is not prime. and we can leave the loop. We're all done. If we get all the way through this loop and we never switch it back over to not prime, that means it is prime, and this is a prime factor of this number. We just need to keep track of them so we can find out whether it is the largest one. Okay, let's go code that out. I've got Visual Studio Code pulled up. I have a file called pe3.py, and here is the description that Project Euler gives us. It says the prime factors of 13, 195 are 5, 7, 13, and 29. So they have already solved the problem based on our pseudocode. They took just a way smaller number, found all the factors, at the very least it's 5, 7, 13, and 29, and then they took of those factors, which ones are prime? Well, it's these numbers. 5 is prime, it has no even multiples. 7 is prime, 13 is prime, and so is 29. So those satisfy both criteria. They are prime and they are factors. All right, what is the largest prime factor of this number? And I put the answer here. If you want to pause me and try on your own and see if you can come up with that, this will give you that opportunity. So I've got two numbers defined. This is this number just without the commas, and then I have their smaller number. This is the number we are after, but we can use this to sort of test our answer along the way to see if we can come up with these same numbers, okay? So you can catch up however you need to, if you need to copy that huge number or go to Project Euler or whatever, but we're going to start off with this one. And as I said, the first thing that we need to do here is find all the factors of big num. So that's our first task, and we're going to use a loop to do that. So we will do for I in, we're gonna make a range. We'll start at 2. We don't need to start at 2 because it's obvious neither one of these numbers is divisible by 2, but you have to start somewhere so you can make that decision. And we will go up to big num. All right, so I is going to start off at 2, and then 3, and then 4, and eventually it's going to stop when we hit 13, 195. So how do we know, is it a factor? So is it a factor? Use the modulus operator. So if we're going to do big num mod I equals 0, then this is a factor. The next thing we need to do now is find out if it is prime. If it is, then what we'll do is up at the top here, right below big number, I'm going to make a list of prime factors. You could just keep a variable and overwrite it if it's bigger than what used to be there. I kind of like this because we can see all of the prime factors this way, and then we can just grab the biggest one at the end. Okay, so this is a factor. Find out is it prime. Well, how do we do that? Well, we're going to define a function. We're going to do def am I prime, and we're going to expect I. We call it I down here. I is the factor of whatever number we happen to be on our way up to that huge number. So that's what we'll stick with. Well, is this number, which is a factor, prime? So we're talking about I. So we're going to need to loop from the number 2 up to I, just like we did down here, but we want to do the reverse. We want to make sure that nothing is divisible evenly. So for, we'll call it this time n, in range, we're going to go from the number 2 up to I. All right, we'll say check if I mod n is 0. If so, not prime. So that's just what we'll do. We'll do if I mod n equals 0, then we are going to make a Boolean up here. So inside of our am I prime, the first thing we'll do is we'll have a variable called is prime, and we'll set that to true. So we will assume the number is true until we find it's not. Okay, sorry, that should not be true. Assume the number is prime until we find out that it's not. So down here, we're looping through, starting from 2, going up to I. If I mod n is 0, then we're going to flip the switch here. We're going to change is prime to false. We can go ahead and break. Let's put a note in there. No reason to keep checking it's not prime. We don't care anymore at this point. And this is going to be really, really helpful because we'll work with prime numbers occasionally in Project Euler. Any number that's divisible by 2, which is half of all numbers, is not prime. Which means we never have to go past 2 on half the numbers, which is the first number. So this is going to save us a lot of operations. If we come down here, right after we are done with our loop, but before the function ends, so we'll put it in right here, we are going to return is prime. And is prime at this point is going to be true or false. It will be true if this never happened. It will be false if it did happen. So down below here, let's call is this factor prime. We're going to call am I prime, and we are going to send up the number I. Let's do this. Let's print off. We'll go into F formatting mode here. Let's print off is the factor prime. In front of that, let's actually print off the number I. So as we loop through, and we're going to big num right now, I have set at 13,195 because that will be very fast. This is going to determine, right, loop through, check to see if it's a factor. If it is a factor, then call mi prime, send the factor up. You will get back true or false, and print off whatever you happen to get. So let's come over, and I am going to run Python 3 against pe.py, and there we go. So these are all the factors of 13,195, and is 5 prime? It is. Is 7 prime? It is. 13, 29. We get to 35. Well, 35 is divisible by 5, so we can already see that that one's not. 65. Same thing here. Okay, as we go through the list, everything after 29 is false, which means it's not prime, which means it found something it could divide by. 145 is divisible by 5. Okay, same down here. So that means that these are the prime factors, and if we come back over and check our work, sure enough, that's what they have, 5, 7, 13, and 29. Okay, so it looks like our code works. How exciting. I'm going to comment out line 8, and I'm going to bring in line 7. So we're going to loop up from 13,000 to 600 billion. So it will take longer, but let's see what happens. Okay, it is slowing down significantly. It did get up to, what number is this? 1,000. It got up to 10 million, and then it stalled out here. Okay, there we go. We hit 800 million. We have a long way to go. We're not even to a billion yet. We got to get up to 100 billion. I'm going to close this and go ahead and tell you it's not going to work. All right. In our previous versions, we imported the time module. So up at the very top, I'm going to bring in time. And at the very top of our program here, we're going to do start time equals time.time open close. We're going to scroll all the way to the bottom here. And I'm going to put in another one. We'll do end time equals time.time open close. And we are going to print off, go into F formatting here, number of seconds to solve ... We will switch over into bracket mode, and we're going to do end time minus the start time. Okay, and I am going to come back up to the top, and I'm going to switch back over our big num to 13,195. So let's run this. Okay, it takes a completely irrelevant amount of time. It's 0.0012 seconds, so basically no time. If I bring our big num back in, I am going to start by hacking some numbers off of it. So I'm going to drop after, let's do it right here. Okay, I'm just putting a hash in there, so we're not working with 600 billion, we're working with 60,000. So let's run that. Okay, and we get back 0.005. Let's move our hash 1 to the right. So we've added a 0. How much longer does it take Python? Well, it goes from 0.005 to 0.05, so roughly 10 times. If I move the hash over one more place, so now we're dealing with 8,514. Let's save that, run it again. Okay, it has now moved to 0.59. So every time we add a 0, I'll do it one more time and I'll get it kicked off here. Move it one more place. Okay, this time it's going to take about 5 seconds. As you'll notice the pattern here, we started at 0.005, then 0.05, now 0.59, and now we hit 5.1. So every time we add a 0, it increases it by a factor of 10. We have 4 more zeros to go. So we are currently at 5 seconds. If we add another 0, that's going to hit 50 seconds. Another one will be 500 seconds. And then another one is going to be 5,000 seconds. So again, this puts us at 50. This puts us at 500. This puts us at 5,000. This puts us at 50,000. which I will just do a quick translation for you. On my Mac, every machine is going to be different, but on my Mac, that means it's going to take 13 hours to run all the way through 600 billion. Depending on your machine, it could be faster, it could be slower, but every Project Euler problem should be solvable in 1 minute. So, back to the board. So, as we already saw, this number is simply too big, even for Python. There are just too many iterations, having to loop all the way up to it, and then having to loop all the way up to each number that turns out to be a factor. It's just too many computations. It reminds me of the movie The Imitation Game. If you haven't seen it, it is about a British cryptographer, mathematician, computer scientist named Alan Turing. He is trying to decrypt the German messages as they're being passed around during World War II. The system that the Germans used was called Enigma, and he builds kind of the first general purpose computer. It doesn't have a really specific purpose, it can do lots of things. And no matter what he does, it just simply has too many possibilities. There are too many permutations for what the cryptography could be, or how to decrypt it. And at one point, he finds a little hole. I don't want to give the movie away, but he's able to reduce the number of possibilities exponentially. And it goes from what would take days before the Germans switched the cryptography key to minutes. And he's able to decrypt it. That's what we need to do. We cannot be going up to this number, or we have to figure out how we can check less primes or something. Okay? And there is, in fact, a way. If we look at the number 10, okay? 10 is an easy number to try. It's not divisible by 9. It's not divisible by 8 or 7 or 6. It is divisible by 5. So if we do 5 into 10, it will go 2 times. 2 times 5 is 10. We get a 0 back. So 5 is a factor. Do you notice anything, though? 5 isn't the only factor that we just found. We also found the number 2. Every single time we find a valid factor of the number, we've actually found 2 because there's always the other side of it. So if we look at the number, let's get a bigger number. We'll go up to 100. And we'll start at 2. So there's 2 and there's 50. 2 times 50 is 100. Those are both factors. 3 is not. 4 will go in 25 times, so those are both factors. 5 will go in 20 times. Do you see a pattern here? Right? As we get bigger on the left, we get smaller on the right. We get to the number 10, and 10 will go in 10 times. That is all of the factors of the number 100. What relationship do you see between the number 100 and the number 10? What is 10 in relationship to 100? The answer is it is the square root. Okay? We do not have to ever check past the square root, because if we have found on the way up to the square root a factor, it means we have found its correspondent on the other side. So we check 2, we got 50. 50 is bigger than 10, but we will find 50 before we get to the square root because we already found 2, and 50 is the other side of 2. Right? Same with 4 and 25, same with 5 and 20. We get to the square root if that is a factor, right? We only found 1 in this case because it happens to be the same. We don't have to check anymore. Do you see how awesome this is going to be? Instead of having to check all the way up to the number 100, we only have to check up to the number 10. This is going to make a big difference. So let's give it a try. We are interested in our outer loop. We're looping from I in range from 2 to big num. We don't need to go to big num. We only need to go to its square root. So up at the top, I am going to import the math module. The reason for that is because that's where the square root function is at. Right before we start our loop, I'm going to make a new variable, and I'm going to call it top num, and we'll do math.square root, and we will hand it big num. That's probably going to return a float, so let's do math.floor, which will round down, and then just for good measure, let's add 1. This won't increase the amount of time at all. So instead of looping up to big num, we're going to loop up to top num. And then the other thing we have to do, because we get 2 different factors every time we check, we need to grab the other one because we only have the I. So let's put in there. We've got this as a factor. We're also going to do get its pair. We'll make a new variable called j, and in order to find the other side, we just have to do the reverse division. We do big num divided by I, which we know is even because it just returns 0 right up here. That will give us the other side of the number. And this is, because we're doing division here, it's going to add a 0.0 at the end just for precision's sake. So we're going to do math.floor here as well. That will guarantee that j is just an integer. And we know it has to be an integer because we just checked it here on line 35. Now we can find out if it's prime. I'm going to copy these two lines here, and I'm going to paste them in, and we will run the exact same thing on j. So these two lines right here are getting the lower one. So in the case of 100, this would be checking 2 and printing off 2. Now we're going to print off the other side, which is 50, and then we'll print off 50. So let's give that a try. Run our code. Okay, 71, this is the other side. If you multiply these two numbers, it gets us that 600 billion number. 71's prime, this isn't. 839 is prime, this one isn't. The big news here is that it took 0.08 seconds, which is staggering compared to 13 hours, at least on my computer. So let's comment these out. Let's append to, we've got list of prime factors right here. Let's put that, we'll do list of prime factors, append. We want to know, let's move it up a little bit here. So right here, if is factor prime, then we're going to append the factor, which is I, to our list. So this is the list of prime factors. We're going to do the exact same thing right after this. If, check the exact same thing because we just overwrote it. If that is prime, then we're going to grab list of prime factors. We're going to append j to that list. And when we are all done, list of prime factors, we will have checked both the smaller and the upper to see if they are prime. Let's print off right here, list of prime factors, moment of truth. Here they are. 6857 is the largest one. If we come back over, the answer is 6857. So we have succeeded. A job well done. Lots going on here. If you want to try and find a more precise way or an even more efficient way, let me know. But great job coming all the way to the end here.